Hello students. So this is Springs part 7 and we were discussing about surge in the springs. So as I have told you that whenever we compress a spring or apply a force on the spring, for example this is your spring and I am applying a force from the top side, the deflection of the coils will be gradual. That is the deflection will travel from upper coils to lower coils gradually, and this deflection propagates from upside down, and when it reaches down then this deflection moves back towards upwards. So if the direction of travel of the deflection, the time taken by the deflection to travel from top to bottom and bottom to top will be equal to the time frequency of the load applied, then the resonance will occur in the spring. Resonance is the condition when the frequency of externally applied load becomes equal to the natural frequency of the spring. In that condition, resonance will occur. And what will be the result of the resonance? The result of the resonance will be very high amplitude of the spring, and due to this, the spring may fail. So this is actually undesirable condition. That is, we do not want to have surge in our springs. So the result of surge is very large deflections of the coils and correspondingly very high stresses. So when your spring will have high deflections, it will also have high stresses. Under these conditions, it is just possible that spring may fail. So this phenomena is called surge. Surge in springs may be eliminated by using following methods. First one, by using friction dampers on the center coils so that the wave propagation dies out. So we can use friction dampers uh, by using springs of high natural frequency, by using springs having pitch of coils near the ends different than at the center to have different natural frequencies. So means we can vary the natural frequency of the spring. That is, at the center it will have some different natural frequency, at the top it is having different natural frequency. By doing this we can stop the resonance, because resonance occurs when the frequency becomes equal. So by changing the frequency of the spring, we can prevent the phenomena of surge. Next is buckling of compression springs. It is it has been found experimentally that when the free length of the spring is more than 4 times the mean or pitch diameter d, then the spring behaves like a column and may fail by buckling at a comparatively low load. So when the free length of the spring is more than 4 times the pitch diameter of the coil, means spring is very tall or very thin, we can say at that point buckling of the spring will happen like this. If the spring is having free length more than 4 times its diameter, then the phenomenon of buckling can happen. The critical axial load that causes buckling may be calculated by using the following relation. So at what load the buckling will happen can be calculated by this relation, K into KB into LF, where K is equal to spring rate or stiffness of the spring. So this is stiffness of the spring, load upon deflection. LF means free length of the spring. KB means buckling factor depending upon the ratio of length and diameter. Next phenomena is nipping in leaf springs. A leaf spring commonly used in automobiles is semi-elliptical form. So you have seen this leaf spring in many automobiles, heavy duty automobiles. It is of semi-elliptical shape. It is built up of a number of plates known as leaves. So these plates are called leaves. The leaves are usually given an initial curvature or cambered so that they will tend to straighten under the load. So when this spring is applied in the automobiles, its tendency is to straighten under the load. So this is load acting 2W at the center of the leaf spring. The leaves are held together by means of bolt passing through the center. So this is the bolt passing through the center which keep the leaves together. The longest leaf is known as main leaf or master leaf. has its ends formed in the shape of an eye through which the bolts are passed to secure the spring to its spot. So these are eyes in the longest leaf. This is called master leaf. So this is used to hang the, or we can say to attach the leaf spring to the automobile. Usually the eyes through which the spring is attached to the hanger or shackle are provided with bushings of some anti-friction material such as bronzes. So in these eyes we use some anti-friction material, so like bronze. The other leaves of the spring are known as graduated leaves. In order to prevent digging in the adjacent leaves, the ends of the graduated leaves are trimmed in various forms. So you can see these are graduated leaves and their ends are trimmed, like these are given some shapes after trimming so that they don't dig into each other. Since the master leaf has to withstand vertical bending loads as well as loads due to sideways of the vehicle and twisting, therefore due to the presence of stresses caused by these loads, it's usual to provide two full length leaves and the rest graduated leaves. So since the larger leaf, that is the master leaf, will be acted upon by bending as well as torsion as well as side thrust, therefore we will provide two full length leaves and other are the graduated leaves. The stresses in the full length leaf is 50% greater than the stresses in the graduated leaves. So actually the stresses in the full length leaves is 50% greater than the stresses in the graduated leaves. Equalized stress in the spring leaves, that is nipping. This phenomena is called nipping. When we equalize the stress of the master leaf and graduated leaves, this phenomena is called nipping. How this can be achieved, let's see. So we have already discussed that stress in the full length leaves is 50% greater than the stress in the graduated leaves. So in order to utilize material to best advantage, all leaves should be equally stressed. This can be done by nipping. So what is nipping? Here is an example. By giving a greater radius of curvature to the full length leaves than graduated leaves as shown below, the leaves are assembled to form a spring. So you can see the master leaf is given a greater radius of curvature and the graduated leaf have a less radius of curvature. So there is a gap between master leaf and graduated leaf before we attach them with the bolt. So this gap is called C, or we can say this gap is called nipping. So why this gap is given? By doing so, a gap or clearance will be left between the leaves. This initial gap is known by C. It is called nip. When the central bolt holding the various leaves together is tightened, the full length leaf will bend back as shown dotted and have an initial stress in a direction opposite to that of the normal load. So what will happen when we when we connect these leaves with the help of bolt? The full length leaf will be acted upon by a stress which is acting downward, means it is acted upon by a stress which is opposite to the actual stress acted on the spring by the vehicle. So initial stress will be given to the full length leaf but in opposite direction. So this opposite direction stress will counter the main stress and reduce the effect of main stress. So the graduated leaves will have an initial stress in the same direction as that of the normal load, but the gradual leaves have the stress in upward direction which is same as that of the normal load, but full length leaf have the stress in opposite to the main stress. Therefore main stress will be reduced by some amount. So in this way we can reduce or balance the stress between the master leaf and the graduated leaf, and this phenomena is called nipping. When the load is gradually applied to the spring, the full length leaf is first relieved of initial stress and then stressed in opposite direction. So consequently, the full length leaf will be stressed less than the graduated leaves. So in this way, we can reduce the stress. Okay guys, so these slides complete all the concepts of the springs, and we have discussed some of the important numericals. We will cover more numericals as well. So this completes your chapter of spring. Okay guys, thank you.